Hi everyone. So today I'll talk about can large language models reason? We know large language models can do a lot of stuff like question answering, they can do summarization, they can follow instruction, they can solve math problems. But can they reason? What is reasoning? Okay. Why do we talk about reasoning in context of large language models? They were never planned for reasoning tasks, right? So I'll answer all these questions in this talk. And as you know, I make all the slides available, so feel free to go to the link in the description and get the slides for this talk. So why do we talk about reasoning in context of LLMs? I don't remember we talked so much about reasoning before the large language models appear. For example, when we had sequence to sequence architectures, recurrent neural networks, attention based models, we did not talk about reasoning so much. But now it has become a reality, and this is one of the main research areas in LLMs. And the reason is that reasoning is one of what is called emergent property of foundation models or large language models. Emergent properties are properties that are present only in large models, but they don't appear in smaller models. So there is a threshold beyond which the emergent properties starts to appear suddenly. And they are not only dependent on the size of the model, but they depend on, for example, training flops, model parameters, and training data size and quality, of course, also. So if you look at, for example, any of these plots, you can see that after a certain threshold, suddenly the results become very good compared to before that threshold. Okay, so that's the reason why reasoning now is talked about in terms of LLM, but it was not there before LLM era. So, as we know, most of the large language models are based on an architecture called transformer architecture. And this architecture was presented in this paper, which is a very famous paper, Attention is All You Need. And in some of my talk, I'll explain what it means, like attention is all you need, because before this paper appeared, there were many other things that were used in addition to attention. Actually, attention became common in sequence to sequence models, but later people realized that everything else they do is not so useful. Only attention can do the job. It's not as simple as that, but yeah, that's a summary of it. Okay. And most of the architectures are based on most of the LLMs are based on this. So what is attention? Attention is simply the focus. It allows the model to focus on the most important data that it needs to come up with the result. Okay, for example, in the upper left corner, the animal didn't cross the street because it was too tired. So when it talks about it needs to focus on the animal because it refers to the animal. However, in another sentence, the animal didn't cross the street because it was too wide. In this case, it refers to the street and not the animal. So the model needs to focus more on street. Attention is not a concept in language models also. For example, in the bottom example, when the model outputs frisbee, in this case, in captioning, it focus on the area of the image that contains the frisbee. Similarly for dog and other signs also. So it's a very broad concept and it's widely used in LLMs. How does the transformer architecture look like? This is an oversimplified picture of what transformer architecture look like. So we have input. Okay, input in this case is a language, and then it goes to an encoder which provides a vector, encoding of the input, and then we have a decoder where we give our target. Target can be, for example, in this case, a star token, and then it outputs the next word, the most probable word. In this case, it's Tokyo. Okay. As I said, this is an oversimplified version of what transformer architecture is. I will cover transformer architecture in one of my talks in the future. The architecture is mainly based on a version of attention called self-attention. Self-attention means that the attention on the data, on the same data. Okay. So, for example, here the encoder consists of several layers of self-attention mechanism. Again, let me remind you, this is a very simplified version. It's actually multi-headed attention. There are positional encoding. There is an embedding. There is tokenization. So I'm skipping all of that. Okay. So the three things that you need to understand here are Q, K, and V. Okay. Q is known as query. K is key. V is value. Okay. So these are the input to the self-attention module. And what are query, key, and value? Just understand that query is like a question that you ask. Okay, for example, what is the full name? Okay, K is the key. In terms of database, it can be the column name. Okay, and V is the value. Okay, the value that comes as a result of that query and the key that was found. Given the table above, and the query, what is the full name? The key will be the name field here. Okay, and the value will be my name, Asim Munawar, in this case. Where does this Q, K, and V comes from? They are just transformation on the input embeddings. Okay, let's say the input embeddings are X. We have three weight matrices here, WQ, WK, WV, and these are basically computed as results of training. So there is no magic going on here. We just train them in a way that they become query, key, and value. I will talk about attention also in more detail in one of my upcoming talks. So let's go to reasoning with large language. So what is reasoning? Reasoning is the process of thinking about something in a logical and systematic step-by-step way. We are not interested in the final conclusion or the decision. We want to know how the system reached that conclusion. There are various types of reasoning. I'll talk about deduction and induction here. Deduction is where we are given few facts, we are given some rules, and we find new facts based on that. In this example, all swans are white, Daisy is a swan, so therefore we can infer Daisy is white. Induction, on the other hand, is where we are given many facts and the system tries to learn new rules. Induction is very similar to how neural networks work. Deduction is very similar to how formal reasoning, logical reasoning system works. So in case of induction, in this example, let's suppose it observes Daisy is a swan and white, Daisy is a swan and white. It observes that many times and it can learn that all swans are white, which might be wrong. It's more probable, but it might be wrong. There can be some swan that is some other color. So before I go into the detail of reasoning with LLMs, there is another concept that we need to understand, that is thinking fast and slow. This is the title of a book by Daniel Kahneman, and I'll highly recommend you to read this book. In this case, he defined two systems working in our brain, system 1 and system 2. System 1 is the unconscious part of the brain that is doing 95% of the task. It's like autopilot, okay, and it's just intuition. We just learn it over time, okay. Things like recognizing an object in an image, we don't need to think about that, right? We don't need to step by step reason about what the object is. We just know that it's a picture of a cat, it's a picture of a car. And simple math operations like 2 plus 2 we can do very easily. We don't need to think about that, right? And system 2, on the other hand, is a rational thinking system where we solve complex problem by planning for them, solving them in a step-by-step way, thinking about them. It's a slow system. It takes effort to solve this, okay. Most of the tasks, like 95% of the tasks, use system 1, but we do need system 2 to solve very important parts of our daily the actions that we take in daily life. For example, this circle that appeared on the screen, if I ask anyone, they will just say it's a red circle, right? We don't need to think about that. We know that it's a circle, it's red. We cannot explain it very well. But let me ask you another task. Plan a vacation. Now suddenly we need to put effort into this. We need to ask a lot of questions. We need to know a lot of things before we can do that, okay. For example, how many people are going, what's the cost, what kind of travel do the person prefers, okay. What are the constraints, any other airline constraints, weather constraints, anything else. So you see, a lot of effort, step-by-step process goes into that. But after you made the plan, you can explain your decision, okay. That's how system 2 works. In real life problems, system 1 and system 2 works in a harmony. For example, in this image, who can go first? First, we need to understand the scene. What are the objects in the scene? For example, traffic signs, what other cars exist, lane markings, and so on and so forth. That is mostly system 1. But once we understand the scene, we need to apply traffic rules. Who needs to stop, who needs to go first comes from the traffic rules of that area or that country. That is system 2 thinking. So we need both in order to make the decision in this case. There is another very important categorization of reasoning that I would like to discuss, and that is formal reasoning versus informal reasoning. Formal reasoning is very systematic, it is logical, it's based on set of principles and rules. Okay. Informal reasoning is less structured. It usually refers to how humans describe something based on their experience and common sense to solve the problem. So formal reasoning is more structured, very reliable, but sometimes it might not be solvable. Informal reasoning is more adaptable and open-ended, okay, but it's less reliable. So in terms of LLMs, at least for this presentation, I'll talk about mostly informal reasoning, because we do know that formal reasoning is something that neural networks and LLMs struggle with. Let me talk about what's the difference between reasoning versus treating large language models as a black box. For example, if you ask this question, Bob has 8 candies, he bought 4 more and distributed equally among 3 kids. How many candies will each kid get? If we just ask it to a large language model, and if it does not make a mistake, it will tell each kid will get 4 candies. We might be happy with this answer, but we would like to know how the model reached this answer. That is reasoning. So we want the steps. So in traditional systems, we first used to do semantic parsing, where we understand all the entities. So Bob Candy ate and Candy's bought, and each kid candy is the question mark, and we need to find out. And then we used to use symbolic reasoning engines to come up with the missing information. So in this case, each kid candy is equal to 4, and then we can use natural language generation to find out a natural sentence to reply back. So you can see the black box versus more step-by-step pre-deep learning or pre-LLM approach. Okay. So let me talk about in-context learning or few-shot prompting. In-context learning is nothing but asking the model in a nice way by showing some examples on how to do stuff. For example, we can ask a large language model to solve a math problem 21 plus 7 directly. But what if we show some examples to the model? So at the bottom we show 4 short prompts, like 4 examples. Okay, 13 minus 2 is equal to 11, and few more examples. Now the model understands that what we want to do is solve a math equation. And here, if we ask 21 plus 7, we can expect better accuracy by showing few examples. On the left hand side, the plot confirms that where zero shot have the lowest result, just showing one example improve the result, and showing few examples improve it even further. So let me talk about chain of thought prompting. It is the most common way of reasoning with large language models. We notice that standard prompting does not perform very well on complex reasoning tasks, for example, common sense reasoning. Chain of thought improves the reasoning capabilities by introducing some intermediate steps in the examples that we show to the model or the prompts that we show to the model. Let me show you an example. Let's suppose in standard prompting we have a question: Alex has 5 cakes, she got 2 more and gave away 4. How many cakes does Alex have? So we will just say the answer is 3. We can give few more examples like 2, 3, 4, as many as we want. In chain of thought prompting, we'll not just give the answer, we'll give the steps also that led to that answer. So in the answer with COT prompting, we can say Alex starts with 5 cakes, she gets 2 more, so she has 5 plus 2 is equal to 7 cakes. Then she gives away 4, so 7 minus 4 is equal to 3, and the answer is 3. And chain of thought prompting can also be used in few shot, one shot, or even zero shot. I'll show you in the coming slides. If we see empirically, chain of thought prompting increased the result significantly. For example, here we have in the center, we have a data set where we want to infer a date from the given context. We can see that by just chain of thought prompting, by giving some examples with intermediate steps or asking the model to produce the intermediate steps, we can suddenly increase the performance drastically over standard prompting. And as I said, we can also do zero shot chain of thought prompting. In zero shot chain of thought prompting, we don't show any examples, but instead of asking the model to give the answer, we ask it to think step by step. Just by asking the model to think step by step, the model gives us the intermediate steps that it needs to reach the conclusion, and then we can ask the model to give us the final answer. Even if you look on the result table, we can see that zero shot chain of thought prompting drastically improves the results on arithmetic dataset. So let me show you an example. So if we ask the model, what is the largest state bordering the Mississippi River? it gives the answer the largest state bordering Mississippi River is Louisiana. Probably it has misunderstood the question and then it gives the wrong answer. But if we ask this question, what is the largest state bordering Mississippi River? Think step by step. That's it. That's the only difference. So it outputs list of states that borders Mississippi River. Then it finds the size of the states. Then it finds the largest state and then it answers correctly. Therefore, Minnesota is the largest state bordering Mississippi River. So you see, just asking zero shot chain of thought, just asking things step by step drastically improved the results. And it also gave us the intermediate step that were used to reach that conclusion. So there are a lot of variations built upon the concept of chain of thought. For example, here the slide shows tree of thought. In tree of thought, it can generate multiple thoughts at the same time. It can even prune low quality thoughts. It can backtrack if it requires, and it can ultimately improve the results on reasoning even further. Okay, so final verdict. Can large language models reason? So I would say yes, for sure. Large language models do show capability of informal reasoning, and they are in many benchmarks shown to be better than non-expert humans. But there are also many issues that we should understand whenever we use large language models for reasoning. One issue is that a lot of benchmark problems that we see are based on math problems. However, in real world, there are many other types of reasoning like common sense reasoning that we need to do. Another issue is that we don't know if all the benchmarks that we are testing with were never seen by the model during the training. So this means if the model have already seen that data set, then it might just be retrieving the answer instead of what we think is reasoning. Okay. So this is a big issue because these data sets are trained on a lot of data, internet scale data. So there is a very serious possibility of contamination. And the third thing is that models might be relying on shortcut, and it might not be reasoning at all in the way that we think. Okay, so thank you. And here are several ways to connect with me. Please feel free to reach out. And as I said in the start of the presentation, I do share all my slides in PPT format at the GitHub repository. So please, if you want to use the slides, you can get them from this GitHub repo, but please do follow the license that I have put at this GitHub whenever you use these slides. Thank you.